Good evening, students. And this lecture we will discuss about the impedance spectroscopy. Okay, so here, like any other spectroscopy, wherein you have uh, in the x-axis you generally have a frequency or a wave number or wavelength, and in the y-axis you have something like absorbance or transmittance. For example, U visible spectroscopy, you have wavelength in nanometer in the x-axis, and your absorbance comes in the y-axis. So the impedance spectroscopy as well is something similar to that. So in your x-axis, actually there are various forms in which the impedance spectroscopy is represented, but basically here we will apply a voltage waveform at different frequency ranging from a megahertz to millihertz or microhertz, and seeing the impedance response of the given circuit. Okay, so the impedance versus the frequency of the voltage waveform. So that's a spectroscopy. Okay, so before entering into the impedance spectroscopy, let's understand certain basics which are needed if you want to comprehend the data that I am going to show on impedance. Okay, so let's look at what is a sinusoidal motion first. Let's take a circle. So we have an arm which is whose length is equivalent to the radius. Okay, so that arm is now rotating. So every time it sweeps an angle, it forms a right angle triangle if we have a perpendicular from the point where it is on the curve to the x-axis. Okay, so when you sweep little more, then it forms another right angle triangle, a little more, one more. So as you can see, what is the sine theta? Sine theta is the opposite side by the hypotenuse. So if you see y, this length I call it as y, is equal to r times sine theta. So r is like kind of a amplitude whose value is modulated with the sine theta. Okay, so let us look at here. So every this height of this uh, opposite side I have plotted with respect to the time or theta. You can see it forms a kind of a sine wave. Okay, now imagine if you have a voltage, the voltage rises like this and falls like this. That means that it is a voltage waveform. So it's an AC circuit because it's alternating circuit. So one time it has a positive magnitude, the other instance it has a negative magnitude. Okay, so now let us look at the voltage and current waveform. Um, let's consider this voltage waveform. So we apply voltage in this fashion. Assume T1 is equal to 1 second, then it is 1 hertz, because this starting from 0 up to 360 degree, it's 1 revolution. So 1 revolution per second is like a 1 hertz. Okay, so what will be the corresponding current response had we applied this voltage waveform across a resistor? So it will be like this. So exactly one wave of current that you would see at time t1. So that means the frequency of your resultant current waveform is also 1 hertz, just like your voltage waveform. But some of the electrical components like capacitor will have a different kind of waveform. For example, when the voltage waveform is at its 0, the current waveform will be at its maximum. Okay, and wherever the voltage waveform is maximum, the current will be at its minimum. So the T1 is here, so this is one full wave. Okay, so there is no change in the frequency, but there is a change in the phase. The current leads 90 degree compared to the voltage. So current leads voltage in case of capacitor. Imagine we have some other electrical compound which is a combination of a capacitor, resistor, and so on. So it may have a waveform like this. Okay, so this is something like 45 degree, right? So these are the characteristics. See, when you apply a voltage waveform, we get a current waveform. So analyzing these two, we can understand the impedance of the given circuit. Let us look at the IV relationship of a battery. So you all know, in case of battery, because it's an electrochemical system, so IV relationship is controlled by the Tafel or Butler-Ulmer kinetics. So the current and voltage are related exponentially. Okay. So always current goes from high potential, this longer line, to the low potential. And what is this? Why this line is smaller? Remember, when we have anode and cathode, the potential of the standard reduction potential of your anode is smaller than the cathode. So this length, this line represents the magnitude. So the anode is smaller and the cathode is bigger in potential. Okay. So, but the electron leaves from the anode, travels to the external circuit and goes to the cathode, which is this long line. Okay. So if you have a resistor, for example, if you apply a voltage across a resistor and keep changing that voltage, how do the current would vary? It will be as per the Ohm's law. I R equal to V, where R is a resistance. So when you change the voltage drop across the resistor, since R cannot be changed, only I would vary. So it would look like this. The slope of this line is R. So it will pass through the origin. Same if you do for a diode in a forward bias condition, so you would see up to certain voltage there won't be any current. After you reach the threshold voltage, you will see a increase in the current with the voltage. Let us look at the let us take a copper wire. Okay, so copper wire, select many points in copper wire. So the potential in all these points will be identical. It is customary to assume that the potential drop across any 2 points in this wire is zero. Although practically it is not so, because it has got a finite resistance, but resistance is very, or the resistivity of this wire is very small. So for all practical people, we assume there is no voltage drop if we pass a current through this wire. So what's the relation between the resistivity and resistance? Remember, resistivity is an intensive property, resistance is an extensive property. This is related by this relation where L stands for the length of the wire, A stands for the area of the cross section of the wire through which the electrons flow or current pass. Um, let me explain this scenario with an example. The resistivity of the copper wire is 1.6 into 10 power minus 8 ohm meter. So let us calculate what is the resistance given the diameter of the wire is 2.5 mm and the length of the wire is 1 meter. So you can easily follow this calculation. This is pi r squared, which is area of the cross section of the circular wire, and you can have that, and you know the length is 1 meter. So substitute in this relation and you get resistance of about 3 milli ohm. Okay, so now let us calculate through this resistance. That means we use copper wire of 1 meter of 2.5 mm dia, and I try to pass 1 ampere current through that. What would be the voltage drop in that length? It will be about 3.4 millivolt. This is very insignificant compared to the voltage of the battery, which is typically about 1.5 volt and above. Okay, but whereas if that wire, imagine, has a resistance of say 100 ohm, that means a resistor. Instead of a wire, if you use a resistor, for the same 1 ampere current, you will have a 100 volt. This is a very high voltage drop. If we have such a high voltage drop, then what that voltage drop? The voltage drop is getting converted into energy, right? So heat will evolve during this process when you try to pass current through this resistor of 100 ohm, and it okay, so you will have a 100 volt voltage drop that causes energy liberation. So for 100 volts of 1 ampere, even your copper wire can melt, so much of heat would be produced. Okay, so it's very clear from the above example. If someone asks you to define what is a resistance, we can say it is obstruction offered to the flow of electron is the resistance. The copper wire offers the least resistance, so voltage drop is smaller, whereas a resistor of 100 ohm offers the highest resistance, so the voltage drop is about 100 volt versus the 3 millivolt that we have seen for the copper wire. So that's very clear. But remember, in case of copper wire, this behaves like a resistor, but resistance is very small value. So if you apply a voltage waveform across that wire, so you'll have a current waveform which comes in phase with the voltage waveform. There won't be any change. Right? So we call that as a resistance. Whereas if you choose other components like capacitor or inductor, there is a phase difference between the voltage waveform and current waveform. In such case, to we report a resistance of such a element along with the phase information, so we call that resistance as an impedance. Okay, so the parallel plate capacitor is represented like this: two vertical lines which are equal in length. Okay, so the capacitance of this capacitor is defined as C equal to Q by V, where Q is the charge which is transported from the one side to other side when you apply a voltage of V volts across this. Okay, that means if you apply, if you transport 1 coulomb applying a 1 volt across this, then it is a 1 farad is the capacitance of this capacitor. Okay, so if I charge the capacitor at constant current, what will happen? So let me modify this capacitor equation like this. So dq by dt is the ampere, so that's the current, and dv by dt is a change in potential with time, kind of a scan rate. So I rearrange the equation like this and I plot the change in voltage, okay, with respect to time, because I am doing the charging of the capacitor at constant current. Okay, and c is a constant, doesn't vary. So you would have a response like this, wherein the as you charge, the voltage will rise, and when you discharge, the voltage will start coming down. So since both charging and discharging are done at the same current and it's a constant, so this time gap from this point to this point, that's called the charging time, and time gap from this point to this point, that's a discharge time. If they are equal, we call the capacitor is ideal. In case if the discharge time gap is smaller than the charge time gap, we call this a non-ideal capacitor, because the charge you have invested during charging is not required during discharging. That means something happened to the charge. Probably the charge has left the plate and entered into the electrolyte. So it's a Faraday reaction. So probably charge is lost by a Faraday reaction. So it's called a leaky capacitor. Let us look at what is a electrode electrolyte interface look like, which we call it as a double layer. So we have an electrode, because of its surface energy and dangling bonds and unsaturation, is going to absorb physically some ions. In this case, a negative ion, anion is absorbed. Okay, its counter ion will be in the next layer. So this layer is called inner Helmholtz, this plane, okay, which passes through the center of this anion is called inner Helmholtz plane, and this plane is called outer Helmholtz plane. Beyond this, you will have a random mixture of cations and anions. The thickness of this layer in which you have the potential developing, correct? So that is about 10 nanometer at the max. So the electric field across this double layer would be about gigawatt per meter, right? Because this is, even if you assume 1 volt that drops across this and it's a distance of 10 nanometer, then if you work out, this becomes about a gigawatt per meter. How do we approximate our electrochemical interface in terms of the electrical elements? So when we have an electrode interface, it can act as both as a capacitor, because it can store the charge on the electrolyte interface, or it can also act as a charge transfer interface, wherein the Faraday reaction will happen just like in battery. So that capacitive nature of the electrode will be indicated by a C, capacitance, or a capacitor, and the charge transfer nature of the electrode will be indicated by a impedance, or by a resistor. Okay, this is actually a resistance. The value of the resistance is proportional to the kind of obstruction offered to the flow of electron during this Faraday reaction. Okay. So this is the impedance due to the Faraday reaction, and this is a capacitor that is present. It has got also an impedance. So this is a circuit which kind of approximates our electrolyte interface. Suppose if I take two electrode setup, then you have one for your anode and one for your cathode, or one for your working electrode, one for your counter electrode. In between the electrode, you have a solution and contact resistance, so they swap here. Okay, these are the two terminals of the battery. What happens in a 3 electrode cell? So in 3 electrode cell, we use a third electrode which we call reference electrode, and we use that only to define the potential. With respect to that, we will apply some potential on the working electrode. But the current that is generated in the working electrode is deposited in the counter electrode. It is not sent through the reference electrode. So the potential of the reference electrode will not vary at all, because we are not sending any current. Okay. So when there is no current passed, then there is no question of Faraday impedance. Okay. And since no current is passed, there is no question of even the capacitance, which is from this electrode. Or we can assume the impedance of this part is negligible compared to the impedance of this electrode electrolyte interface. So we can use serial electrode setup, then your equivalent circuit of your electrode interface will simplify like this. This is for your working electrode, the part of the working electrode which act like a capacitance, and this is a part of the working electrode which act like a resistor, through those parts you have the charge transfer reaction that is happening. And this is the solution resistance. This is the solution that is between the working electrode and the reference, not between the working and counter. Okay, so let us look at how the resistor behave when I apply a voltage waveform. So assume that I am applying a voltage waveform at a frequency of 1 Hz. That means this full wave is completed in 1 second. Then you will have a current waveform following that. That will be in phase with the voltage waveform. Look at the magnitude of the current. I have used this axis both for potential and current. So the magnitude of current is about 0.05 and the voltage is about 0.1. Now I am going to change the frequency, say from 1 Hz to 3 Hz. Okay, but still the magnitudes remain same. There is no change. Okay, what I am trying to say is there is no phase difference between the voltage waveform and current waveform. In addition, there is also no, what to say, change in the magnitude or amplitude of the current and voltage waveform with change in the frequency, which is not true when you go to capacitor. For example, the capacitor's voltage and current waveforms are like this, as we discussed before. But note down, the current here is about I1. So when I change the frequency from 1 Hz to 3 Hz, it is goes to another current I2. So when you increase the frequency, the current that you obtain is greater than the previous frequency. So at 3 Hz, the current that you obtain at 3 Hz is greater than the current that you obtained at 1 Hz. Okay, that means the current leads potential by 90°, and in addition the current changes with the frequency. So how do you understand this? Let us take this equation pertaining to the capacitor. So I sometimes use V or sometimes use E to denote the potential. So what is E? The E is a delta E, which is the amplitude, the height of that sine wave. This is sine omega t. The omega t forms the angle because this angular frequency, which is in radians per second, multiplied by time, so you get in radians, so it's an angle. So this is a sweeping angle. Remember in the first slide I showed how that in that circular motion, how that arm sweeps the angle, right? So recall that. So this is, if you differentiate this, so the sine becomes a cosine, and it is c is a constant. So from this you get omega out, so it is c omega delta e cos omega t. Okay, so what it tells, if omega increases, current will increase. So current is depends on the frequency. Okay, and we can also write a for current we can write a what to say, a waveform like this, where IAC can be like the IAC can be like a delta I cos omega t. Okay, this is the amplitude of the current waveform. Okay, so now we rearrange this equation like this and substitute for IAC, and you get delta E by delta I, which is equal to 1 by c omega. So this is like Ohm's law. IR is equal to B, right? So B by I going to be impedance R, correct? So this is the impedance of a capacitor when you apply a voltage waveform, and that is depends on the frequency. If the frequency omega is 0, that means instead of a AC waveform, if you use a DC, that means a fixed potential you apply, then the capacitor will act like a infinite resistor. That means it will not allow any current pass through the circuit. Okay, because omega 0 means this becomes infinity, so the impedance becomes infinity for that circuit. But if omega is infinity, that means at high frequency, what happens? This turns out to be a at high frequency, this turns out to be a very small number. That means impedance is very small. At such condition, your capacitor will act like a conductor. Current will simply go through the capacitor. Okay. Now let us look at the inductor. It's opposite. In inductor case, current actually trail the voltage by 90°. Okay, so the equation for the inductor is like this, where L stands for inductance. So if I assume for current, because it's trailing the voltage, if I assume a sine waveform for voltage, then for current I assume a cosine waveform. So that becomes like this. So just like the previous case, I substitute for the I rearrange this equation. I substitute for the E, and then I get the impedance delta E by delta A as L into omega. Here too it is depends on the frequency, okay, omega. Okay, this is the impedance of a inductor. Okay, so in the next class we will talk about how to represent a phase and a magnitude together, for which we need to use complex numbers. Okay, so in the complex number you have a real and imaginary part. Okay, so in case of resistance, since there is no phase difference, so the impedance coming from the resistor we call it as a real part. All other things like capacitance or inductance, so the impedance coming from those kind of elements we will put it in the imaginary part. Okay, so we know when you adopt a complex notation, since the phase information also has to be adopted, so the impedance of a capacitor will be 1 by j omega c. J is equal to root minus 1, so multiply by j both in the numerator and denominator. What you would get is zc as minus j divided by omega c. Okay, that means the impedance of a capacitance is negative. Okay, the impedance of a capacitance is negative, whereas the impedance of your inductance will be positive. You can work it out and check. Okay, so in this particular case I have shown a DC potential which is 0 volt here, and here it is 0.2 volt. On top of it I have superimposed a AC potential of certain amplitude. Say this is 10 millivolt, that means 0 to 10 millivolt this side, this is minus 10 millivolt. In this case 0.2 to 210 millivolt this side, 190 millivolt this side, right? This will be the magnitude of this point will be 190 millivolt, but the amplitude is 10 millivolt. But since it is 0.2 volt the base value, so it can go 210 or the other side 190. Okay, would the impedance be same at 0 volt as well as at 0.2 volt? It won't be, but for ideal electrical circuits it will be, but for our electrochemical cell it won't be. Okay, so we will discuss that why is it. Okay, so and then the last concept is a differential impedance. Assume you have an IE relationship like this. For example, electrode that gets passivated. So initially when you increase the voltage, the current is increasing. When the electrode gets passivated, the current drops like this. Okay, so what we are trying to measure, suppose if you try to measure what is the ratio of the current and or potential and current, so that in this case say about 2 ohm. Okay, and if you, what we are trying to measure in impedance spectroscopy is not this, which is just a slope of the curve. What we are trying to measure is a dE by di. That means when I apply say 10 millivolt voltage waveform, what will be the change in the current from its base value. So that is dE by di, that is negative here, and this branch it will be positive. Okay, okay, so negative values of impedance is possible, it's not that it's impossible. Remaining I will talk in the next class. Okay, okay, thank you.